Hi, how's it going? I was going to do a couple of general chemistry problems, but I think instead I'm just going to go watch some video trailer and you can see my reaction to it. How about that? That'd be better? Because I quit. You know, it happens to everybody, right? I mean, the History Channel was good on history. Now it's UFO truckers from Antarctica. I don't know what the show now. And don't even get me started on TLC. It's just brain droppings. That's where the real money's at, right? No? All right. Did I miss that boat? God, I should have. Yeah. Reaction trailers. That's the thing that I think finally broke me as a middle-aged man, because I thought I was still cool. I was never cool, but cool on like what's going on. I mean, because the job I have kind of helped, and me having a teenage son helped. I mean, pop music I never really got, but that's okay. I don't need to know the Nene song to not feel old. But, and you know, the whole Let's Play videos, I get that. That's cool. But yeah, watching some dude watch something else that I don't know, that might be the one that finally breaks me as an old man. I don't know. We'll see. But I don't know. I got these notes laid out. I guess we'll go ahead and do the chem problems. So for the general one, guys, how you doing? We're going to do a little bit of stoichiometry, because you can never get too much stoichiometry, or you can never practice too much of it. So that's what we'll do a little bit. And hopefully you're practicing yourself. You're not just watching people do it on this thing, because it'll never get you anywhere. I watched Michael Jordan play a lot of ball in the 80s, and my jump shot is still crap. So, you're right. So we're going to do a couple of just basic stoichiometry problems, sort of gram to gram kind of things. But actually, before we do that one, I want to start with just a simple mole to mole conversion. So, for example, take you know, this reaction between copper and nitric acid. Right. Let's say you have 3.3 moles of nitric acid that you want to make, and you want to know how many moles of NO2 this can also be produced. Right. So you're starting with moles of HNO3, and you want to convert it to moles of NO2, nitrogen dioxide. So remember, do a mole to mole conversion. You just look at the equation that goes with whatever stoichiometry problem you're dealing with. And it looks like that for every one NO2, we need 4 nitric acids to react. I think I said nitric acid was a product a minute ago. Forgive me for that. That's what happens when you read the question backwards. But yeah, nitric acid and NO2, they're 4-to-1 in this reaction. So that's your conversion factor. And when you set it up this way with the nitric acid on the bottom, that unit drops out, and you're already at the unit you want, which is moles of NO2. So you do the math, and you get 0.83. Now let's compare that to a problem where you actually start with 3.3 grams of nitric acid, and you want to know how many grams of NO2 you can make. So again, with any stoichiometry problem, now you start with the unit you're given. And we're given so many grams of nitric acid. So before you can actually do any kind of conversion from one substance to another, you need to convert what's given to moles. That's the first step of any stoichiometry problem. Take what's given, convert it to moles. So anytime you want to convert between grams and moles, that's molar mass. So we divide by the molar mass, that gets us into the mole unit. So at this point, we're in units of moles, which is the same place we were at previously. So the next step is the same as before. You look at the chemical equation, and it's still a 4-to-1 ratio because it's still the same reaction. And again, you set it up just like before. And now, like before, you're in moles of nitrous dioxide. This time the question asks for grams. So anytime you want to go between grams and moles, moles to grams, you always use that chemical's molar mass. So using NO2's molar mass, that gets us into the unit we want, and that gives us the answer in grams of NO2. So you compare the two, and again, notice that you only use molar mass when you're trying to convert between grams and moles. You know, a lot of times when I see students try problems, it's weird. They'll sometimes get the gram to gram one because that's the one we do the most in that chapter. But when you just step back and say, okay, just do mole to mole, they start trying to fudge in the molar mass because they think they need to use it somewhere. Kind of like a couple of sections before that, before we get into reactions, they'll start fudging in Avogadro's number because they think they need it to use it somewhere. If you're doing that, then you really still don't get the unit conversion idea. Remember, the only time you're going to use molar mass is to go between grams and moles. Once you're in moles, you don't need molar mass if you're doing a stoichiometry problem. If you're trying to convert from one thing to another, remember the way you do that is using moles and that chemical equation that's given to you. And the thing that'll help there is, remember, always think about the coefficients in terms of moles. You know, it's not one atom of copper reacting with 4 molecules of nitric. You know, it's a mole of this reacting with 4 moles of that. And until we get to molarity, which I'll do in the next video, that's the two main conversions you're dealing with up to this point. You know, gram to mole, vice versa, using molar mass, or mole to mole. And in stoichiometry, that mole to mole conversion, you always use the chemical equation that's given. Again, Avogadro's number, moles to atoms or molecules. We don't do that a lot once we get into stoichiometry, because again, we usually think about things in the mole scale. So again, at this point with the unit conversion reaction math, we're really doing 2 conversions. 3 if you count Avogadro's, which you're not going to see a lot, probably at least not until your final exam. All right. So a little more about stoichiometry probably next time. I don't know, I said it, I'd do it, so I guess I'm committed. Or maybe not, I don't know. This isn't like a Aaron Sorkin TV show. I mean, I can change my mind and nobody will care. And by the time they do, it's probably way too late. But anyway, on to General 2. So, General 2, guys, how you doing? Did you enjoy that last little trip down memory lane for General 1? No? You probably didn't. You just skipped ahead? That's okay. For you guys, we're going to do a little bit more with kinetics, and we're going to look at some math using the Arrhenius equation, which... the Arrhenius equation, who also gives us a definition of acids and bases a little later on, he also did some kinetic work, and he came up with this equation that we call the Arrhenius equation, which originally is written like this, where the K is your rate constant, which we talked about with our rate law discussion. A is this constant called a frequency factor. We don't usually do much with it in Gen Chem. EA is the activation energy, which we talk about or introduce with collision theory. Remember the peak of that, your hump in your energy diagram. R is your gas constant, but here we use the version with joules per mole Kelvin, not the 0.082 one that you learned back with the ideal gas law. And T, as it usually is a temperature in Kelvin. In general chem, we usually don't do a lot of calculations with that particular equation. We usually modify it a couple of ways. One way is in what we think of as the linear version or form of the Arrhenius equation, because if you write it that way, it's in a linear equation, y equals mx plus b, although I got the mx and b flipped because I just think it looks nicer. But usually use that version for more laboratory based stuff. You know, if you plot, since it's a linear form, you plot natural log over the inverse of temperature, natural log of the rate constant over the inverse of temperature. That'll give you a straight line, and the slope will be negative, the negative of your activation energy divided by your rate constant. So it's a way to experimentally determine the activation energy of a reaction if you're able to do a reaction at different temperatures and measure its rate constant. On the lecture side of things, we tend to use what I call the 1-2 version of the Arrhenius equation, which again, both of these are derived from the one I showed you a minute ago, but I'll skip the derivation. It doesn't matter. We'll save it for time. So a typical way that you use this equation is kind of like you use some of those gas law equations, speaking of the ideal gas law, but not the ideal gas law, the ones we talked before. You remember there's a lot of 1-2 equations there with Boyle's law, Charles' law, where if you had a gas under 2 conditions, if you knew 3 of the 4, you could calculate the 4th. Kind of the same thing here. Although you do also need to know the activation energy. But yeah, if you can measure a reaction at 2 different temperatures and measure its rate constant, then, or if you can measure it just as at 1, you can predict what it should be at the other. And I'm babbling on, I could just show you what I'm talking about. For example, let's say you have a first order reaction that has an activation energy of 18.2 kilojoules, and the rate constant is 0.332 at 25 degrees. All right, so we know the rate constant at that temperature. We can use this equation to figure out the rate constant of some other temperature. Let's say 95 degrees, because why not? So yeah, if you look at what's given in the equation, or what we have in the equation, and compare that to what's given in the problem, we have our K1 and K2, and it can be either set of data, just which you label as 1s and which you label as 2s don't matter, just don't flip-flop them. So if we call K1 0.332, T1 is going to have to be the temperature that goes with it, 25. Although remember, we calculate in Kelvin, so we got to convert that to 298 Kelvin. Right, so K2 will be the thing we're looking for at T2, 95 degrees, or 368 Kelvin. And again, the activation energy is also known. R is a constant, so yeah, we have everything but the thing we're looking for. So you start by plugging in what you know. And so we plug in our K1 and our 2 T's. When you plug in your activation energy, be really careful, because remember, flip all the way back. The gas constant is in units of joules per mole Kelvin. But a lot of times activation energies are given in kilojoules. So remember, when you plug in an activation energy, it has to be in kilojoules. Right. And I actually skipped animation. Oh well. So now that we plug in your gas constant, plug in the activation energy in the proper units, now you can start solving for K. So everything on the right side gets calculated to negative 1.397. And remember, to get rid of the natural log, we just raise e to both sides. I think that's the proper way to say it. Math folks can correct me. So that gives us 0.332 over K2 is equal to e to the negative 1.397, which turns out to be 0.247. And eventually you make your way down to a K2 of 1.34. So one thing to kind of notice here is that, notice that at the higher temperature, the rate constant did go up, which is usually indicative of the reaction going faster. So that answer makes sense. Kind of like back when we did the Boyle's law, Charles' law, all those gas law problems. You know, it's a way to kind of sanity check, you know, if is the thing we calculated going in the right direction. You know, for Boyle's law, if you calculated a pressure when you increased volume, or decreased volume, I guess, did it go up or did it go down? So here, I mean, increasing the temperature should have increased the rate constant, and it did. I keep skipping all around and babbling. So. But for the most part, if you look back at this, again, we have everything in this equation except the thing we're looking for. So it's just a matter of plugging everything in and solving for the thing you want, K2 in this case. The main thing to watch out for is just make sure your activation energy is in joules per mole, even if it's given in kilojoules. And I guess also make sure you use the correct version of R, but the kilojoule joule thing for EA is the thing I see students trip up on a bit the most. So one more, if I can not blob through it. Not that one. There we go. All right. Let's. This is problem P8 in my kinetic chapter in my book. Cheap plug. Let's say I have a reaction with a rate constant that's 0.053 at 25 degrees and 0.103 at 66 degrees Celsius. With that, we should be able to figure out what the activation energy is. So again, you start with the equation that you think you're going to need. We're given two sets of K and T. And again, it doesn't matter what you label as ones and what you label as twos, as long as you don't get them flip-flopped. So if we'll call the ones that were given first are K1 and T1, because why not? The second set that was given, we'll call those two K2 and T2. And so it doesn't matter which ones you label, just don't get them flipped. Like if you make this one K1, don't make this one T1. That's what I meant by getting them mixed up. Otherwise, doesn't matter what you call ones or what you call twos. So again, the R is given. We know the value of the gas constant. We have everything we need to solve for EA. So you just plug all that in and you solve for your unknown. And we just, as we slowly make our way to that, we'll eventually get an activation energy of 13.6 kilojoules. Or 13,600 kilojoules, however you like to do it. So, so you can see for that equation, some of the Arrhenius stuff, it is basically what some people call plug and chug type of calculations, which is a lot of the non-conversion math that we end up doing. Like general one, if you're for some reason just watched all that, yeah, we'll get outside of conversion math a little later. But for the most part, it's either conversion math or plug and chug algebra. And you plug everything into the equation except the one thing that you're given, or you're asked about. I don't know. Me can't talk so good right now. But it's just knowing what equation to use and how to use it. But even if you're not entirely sure, just if you think it's that one, just check it and see, you know, say like we did a minute ago. Okay, we got this, we got this. Yeah, we got everything except the thing they're asking about. So this is probably the one I need. So that's it for today. So I will see you some other time. Yeah, if there's some things that you actually want me to talk about that I'm not talking about, maybe I'll do it. You can leave a comment in the channel page. I think I'm going to keep all my comments there because I'm starting to get a lot of videos and I ain't got time for checking all of their videos. I'm not talking very good right now, am I? So I should probably shut up.